Alright, so in this video, we are discussing Chapter 7, Chemical Reactions and Quantities. And the topics we're going to be discussing are first, how to write equations for a reaction and the different types of reactions, specifically the oxidation reduction reaction, and then we'll define mole, how to calculate mole mass and use it in problem solving, especially problem solving with chemical equations, and mass calculations. For the reactions, this is called as stoichiometry, this particular topic. And then what are limiting reactants, percent yield, and then finally the energy in chemical reactions. So these are all the subheadings, and it is one of those long chapters, and it does require a lot of math that is carried over from the previous chapters. All right, so some of those math skills are about percentages, about solving equations, and knowing how to write numbers in scientific. And then sig figs, of course, using those sig figs in our calculations, writing and using those conversion factors, knowing your energy units, especially for the last section of this chapter. And then from the previous chapter, how to write the formulas of the ionic and molecular compounds. So a chemical change is when the identity of the original substance is fundamentally changed and then a new substance forms. This new substance is different because its formulas are different, its property is different. So here in this picture you can see nice shiny bright iron, just iron nails, and then you see this dull reddish rust developing on the nails. All right, so the component in iron in the nails was just iron. All right, just the iron atoms, and now it has rusted by getting oxidized from the oxygen from the air, and it's no longer the original iron. It's now Fe2O3, iron 3 oxide. Okay, now iron 3 oxide has different properties, different substance compared to elemental or the atom of iron. Okay, and the other thing, key thing to note here is the color change definitely indicates that something has fundamentally changed. But during a chemical change or a chemical reaction, atoms are not really destroyed. They get rearranged. Okay, so mass cannot be created or destroyed, which means that atoms cannot be created or destroyed. So in a chemical reaction, they're getting rearranged. So in a chemical change, how you can tell a chemical change has happened, like the rust, when silver tarnishes, you see that black stuff. This was silver, just pure silver, silver atoms, and then a sulfur from the air has joined up with those silver atoms to form silver sulfide. Okay, so you can see a color change, or when you add vinegar and soda bicarbonate, sodium bicarbonate, you see bubbles forming, or when you drop an antacid into water, you see bubbles forming. Those indicate, again, a chemical reaction is occurring. All right, a chemical change is occurring. The identity of the original substance is changing. Or if you see it was a clear transparent liquid solution which was transparent to light, and then you see some cloudiness after you mix those solutions together, that indicates a chemical reaction has occurred, because you can see that cloudiness, which is a solid or a precipitate coming out of solution. Or you mix two things together and suddenly the test tube in which you mix them, or the reaction vessel gets hot, or it gets cold. All right, so that is either heat is being produced or it is being absorbed, and that also, those heat changes indicates that a reaction is occurring, a chemical change is happening. So here in this particular equation, you can see carbon from coal reacting with the oxygen from the air to form carbon dioxide. So none of the atoms are destroyed. The carbon is transformed now into carbon dioxide. The oxygen, the diatomic molecule of oxygen from the air, joins up with the carbon. All right, so one carbon here, one carbon on the other side, the two oxygen atoms, and you have the two oxygen atoms. So you can see that a chemical change, a chemical reaction, is just a rearrangement of the atoms. They are not being destroyed. All right, so when you write an equation for this, the forward the reaction is shown with an arrow. These are the reactants on the left side of the arrow and the product on the right side of the arrow, and the arrowhead is pointing towards the direction of the reaction. All right, sometimes you also indicate the state, or not sometimes, but most times you also indicate the state in which those reactants and products are. All right, carbon is a solid, so you would put parenthesis lowercase s. Oxygen is a gas, so you would put parenthesis lowercase g. And carbon dioxide is also a gas, and then you would also indicate that with a parenthesis lowercase g. All right, sometimes you also put a triangle on top of the arrow, indicating that heat is involved to get this reaction going. All right, so the triangle indicates heat being supplied to get the reaction moving forward. All right, so the reactants are on the left side, products on the right side. The arrow separates those reactants from the products and indicates the direction of the reaction. This delta, or the triangle, indicates heat is used to get the reaction going. If you have an AQ, parenthesis AQ, besides a reactant or a product, it means that they are dissolved into water. Right? If one of the reactants or products is a liquid, then you use the parenthesis L. So these are some of the symbols used in a chemical equation. You use plus sign to separate out the reactants or products that are either reacting or forming. This is the arrow showing that it is directed from reactants to product. You have the triangle that indicates that the reactants are getting heated, heat is being supplied, and then you have the various symbols, the parenthesis S, showing the state in which either the reactants or products are, parenthesis L, liquid, parenthesis G is gas, and parenthesis AQ means that one or more of the reactants or products are in the aqueous state, which is dissolved into water. So according to the law of conservation of mass, mass cannot be created or destroyed, which means atoms cannot be created or destroyed. And so the atoms are just getting rearranged. So the numbers of each type of atoms on the left side must match up with the numbers of those atoms on the right side. All right, so the reactant atoms must equal the product atoms. All right, so first start by writing correct formulas. All right, so this is why the knowledge that you gained from the previous chapter is important here. You need to know how to write the correct formulas for the reactants and products, and then you count up the atoms on each side. All right, and make sure that they're balanced. When you're balancing, you're using coefficients to balance the elements. All right, you never change subscripts, just the coefficients. Coefficients are the numbers that are found in front of the formula of that element or compound. And then check the final balanced equation to see that everything is in order, that all of the atoms are properly balanced. All right, so here in this reaction, aluminum is reacting with sulfur to form aluminum sulfide. All right, so the way you have to balance this is, if you have one aluminum and two aluminum atoms here, make sure that those are balanced. So the numbers you cannot change are these, the subscripts. Cannot change that because that will change the identity of the substance. What you can certainly change is the numbers that happen in front of the reactant or product. All right, you can change the numbers that happen in the front. If you don't see a number, that means it's 1. All right, okay, so 1 is not written, and so those numbers that occur in front of the formula is called the coefficient. Okay, so I can put a 2 over here, that would balance out the two aluminums, and then I can put a 3 in front of the sulfur, and that would balance out the sulfur. Okay, so the final balanced equation is 2Al, and it's in the solid state, plus 3S, also in the solid state, is giving me Al2S3, also in the solid state. So never change subscripts, never change these numbers, only change the numbers that occur in front of the formula. All right, so state the number of atoms of each element for the following balanced equation. Okay, so you have 4 phosphorus here. You have 12 bromines, and 4 times 3, that's 12 bromines. So it is balanced. Okay, so they are all balanced. And state the number of atoms of each element on the reactant and product side for the following balanced equation. So you have 2 aluminums, 2 ions, 3 oxygens, and 3 oxygens. Balance the chemical equation when solid Fe3O4 reacts with hydrogen gas to produce solid iron and water. So this is called as a word problem, and according to the word problem you have to write down what it says. So it says Fe3O4 is reacting with hydrogen gas. Remember, hydrogen gas exists as a diatomic molecule. All right, so you can't write just H, it's H2. Since they said gas, you have to put parenthesis G. Okay, and it says solid Fe3O4, so you put a parenthesis S for Fe3O4, and it produces solid iron, so it's in its elemental state, FeS, and water, and they didn't indicate the state, but water is liquid, so you'll put an L next to water. All right, so produce means those are the products being formed. All right, so you write this down, then make sure everything is balanced. So you need a 3 here, you need a 4 in front of the water. That means you would need a 4 in front of the hydrogen as well. All right, so Fe3O4, 4H2, giving you 3Fe plus 4H2O. That's the final balanced reaction. When you're balancing polyatomics, do not separate out the polyatomics, such as phosphate. Don't separate it out into phosphorus and oxygen. All right, keep it intact as one entity, as though you're only dealing with one element. All right, okay. So you have here in this picture, you can see the magnesium and the chloride ion separated out. They dissolve into water, aqueous, and then the sodium and the phosphate ion separated out. They're dissolving into water. Now, the moment these are mixing, what is happening? The magnesium exchange of dance partners, the magnesium and phosphate are coming together, and they form a cloudy precipitate, a white stuff that comes out. All right, whereas the sodium and the chloride are staying in solution. All right, so when you're balancing this, make sure that phosphate is left intact. All right, we'll stop here and continue this in the next video.